Okay, so what I'm going to do is I'm going to try and show you the kind of steps that you need to go through to solve one of these capacitor circuit problems. I'm not going to use any numbers. I'm just going to show you the kind of approach that you can take, which is applicable to any of these types of problems. For a specific question, there are lots of different ways of approaching it. There are different ways you can do it. Sometimes you'll see an obvious shortcut. You don't need to go through all the steps. But what I want to show you is a fairly general approach. If you don't know where else to start, this is a good way to tackle the problem. If you follow all the steps, you can basically sort out any of the values that you might need to know. So here we've got a circuit, three capacitors, C1, C2, C3, and we'll imagine that we're told what the capacitance is, but we want to work out what the charge on each capacitor is, or what the potential difference across each capacitor is. In other words, to analyse the circuit as fully as we can. The other thing is we've got a battery here. We'll just say the potential difference across the battery we'll just call V. So the first thing I would do is look at it and make sure that I'm clear in my head as to the relationship between the capacitors. Are they in parallel, in series, etc.? And the way I always start doing that is make sure we're clear about the polarity of the plates. So if this is the battery, I know that this is the positive terminal, this is the negative. Anything connected to the positive terminal of the battery is going to be positively charged, so that's a positive plate. Similarly, anything connected directly to the negative terminal of the battery is going to be negative, so those are going to be negative plates because they're connected simply by the wires. And obviously for a capacitor, I know that if this is a positive plate, this is going to be negative. That's negative, so that's going to be positive. This is negative, so that's going to be positive. And then looking at that, that should give me some clues as to the relationship between the capacitors. And what I would always do next is redraw it so that it just is a bit clearer what I'm dealing with. The first thing that stands out to me is that here I've got capacitors C2 and C3. The positive plate of C3 is connected to the positive plate of C2. The negative plate is connected to the negative plate. That's our definition of capacitors in parallel. So I'm going to draw those two in parallel. So that's C2, that's C3. And then how do they relate to C1? Well, the positive plate of these two capacitors is connected to the negative of C1. I've got the positive connected to the negative. That suggests capacitors in series. So these two are in series with C1. So I'm going to draw in C1 like this. And then I need to just connect up the circuit, put the battery in. I'll put it in here. That's positive, that's the positive terminal, that's the negative, and I'm just going to check that I haven't actually changed the topology of the circuit. It's still exactly the same circuit, I've just shifted things around a bit to make it clear that I've got two capacitors in parallel, C2 and C3. I've got those two in series with C1. And you can go around and check that the battery is connected to the positive plate of C1. I haven't changed that. The negative terminal is connected to the negative of C2 and C3, and so on. So this is exactly the same circuit as that one. But this makes it very clear that what I'm dealing with is a pair of capacitors that are in parallel, and that pair in series with C1. So if I want, the next step is now to simplify it step by step. And you do that by looking at a pair of capacitors, for example, here, and saying, well, I could represent those. I could find the equivalent capacitance of these two parallel capacitors. I could represent that with a single capacitor. In other words, I could redraw this circuit. So that would be C1. I'm going to represent this combination by a single capacitor. I'll call it C23. I'm not going to change anything else, so the battery stays in there. And if this has an equivalent capacitance of C2 and C3 in parallel, then this is an equivalent circuit. So I've reduced it to a circuit which just has two capacitors in series. And similarly I can say, okay, well, I could represent C1 in series with C23 with a single capacitor whose capacitance I can work out, and then the circuit would be reduced right down to the simplest possible case where I've got one capacitor there. That's my battery, the potential difference, and this now is, I'd call it C1, 2, 3, or perhaps more sensibly, let's call it C total. It's the total equivalent capacitance of the whole circuit, but expressed as a capacitance of a single capacitor. And from that, because obviously the V here is the potential difference across this capacitor, I could call that V total. I could easily work out the total charge on the circuit as a whole. That's just going to be given by Q total is equal to C times V. So I've reduced it to the simplest possible form of circuit from which I can work out the total capacitance. I can work out, if I know the total voltage, I can work out the total charge. How does that help? Well, using this I can then work backwards through the circuits, filling in the bits I don't know. First of all though, let's just make sure we know how to work out these equivalent capacitances. I've said that C23 here is the equivalent of C2 in parallel with C3. So we have to remember, how do we work out parallel capacitors? It's the simpler version. When it's capacitors, capacitors in parallel is the simpler case, unlike in resistors. But C23 is just going to be given by C2 plus C3. How do I work out the total capacitance here? Well, here I've got C23 in series with C1. So I've got this capacitor C1 in series with my imaginary capacitor replacing 2 and 3. So series capacitance, remember that's where we have 1 over C total is equal 1 over C1 plus 1 over C2 plus etc, etc. So in this case, putting in the values here, C total, well, let's write it properly. So 1 over C total here is going to be equal to 1 over C1 plus 1 over C23, which equals C2 plus C3. So it's a bit of an ugly expression, but it's simple enough to calculate. If I know the values here, I can work out, remember this is 1 over C total, so actually the total capacitance, I'll try and write it a bit bigger, C total is going to be equal to 1 over C1 plus 1 over C2 plus C3, but remember that's all a reciprocal to find C total. And once I've found C total, as I say, if I know V total, I can work out the total charge, or if I knew the total charge, I could work out V, whichever way around the question is phrased. And then if I want to go back and analyse this circuit, in other words, how could I calculate what Q1 is, or Q2 or Q3? Well, I work backwards. Let's use a different colour. So having worked out total charge on the whole circuit, I would go back to this version of the circuit. Now I know the total charge, QT, in other words I know the total charge on these two series capacitors. And this is where I have to remember my important facts. Remember we said about series capacitors, the voltage is shared between them, if you like, but the charge, where I have series capacitors, the total charge is equal to the charge on this capacitor, which is equal to the charge on this capacitor. So Q total that I've worked out is equal to Q1, which is equal to Q23. So I could work out the charge on here, and if I knew the capacitance, I know Q1, I know C1, I could work out V1, for example. And if I know V1, which is the potential difference across here, and I know the total potential difference across here, well, the potential difference across C23 is just going to be the total minus this. So I could work out V23. So I go back to this version of the circuit. So now let's say I've worked out, I know what the charge is on here, I know what the potential difference is here. I've worked out V23, the potential difference across this capacitor that represents these two in parallel. So I've worked out V23, but remember what we said about potential difference across parallel capacitors, it's the same. So actually what I've worked out, V23 is equal to V2, which is equal to V3. So I know the potential difference across these, and if I know the capacitance, again I could work out exactly what charge I've got on capacitor. This would be Q2, wouldn't it? And I could work out, for example, the charge on Q3. So going back to the original circuit as drawn, I can work out all the values I need. I know Q2, V2, Q3, V3, Q1, V1. And I do it using this process of redrawing the circuit so I know what I'm dealing with, simplifying it, working out perhaps the total charge, and then going back. It's a bit like a logic problem, going back and filling in the gaps. What information do I know? How does that allow me to work out? But the key thing is, in order to do it, you have to remember those two key facts about both parallel capacitors and series capacitors, and then you apply it. And exactly how you apply it depends on what you're trying to, what data is the question giving you, what you're trying to find out. But this general approach is the same and will allow you to solve any of these types of problems. As I say, once you get used to it, there are quicker ways of doing it, there are shortcuts, you don't always have to work out absolutely everything. But to start with, this is a good approach.